Hello, welcome to the lecture on Introduction to Shear Wave Imaging. So today I'll be describing different shear wave imaging methods that are used clinically. So here are two that I have here in this table. We first have our set of shear wave elastography methods where the excitation to produce the shear wave is called the acoustic radiation force. And we'll look more into that in the subsequent slides. There are two techniques that I'll also focus on: point shear wave speed measurement and 2D shear wave speed imaging. And using these two techniques, you'll be able to measure the shear wave speed at specific regions of interest in the tissue and the Young's modulus. The second set of techniques that we'll discuss today is called transient elastography. And in this technique, the excitation method would be a mechanical vibration system that will be used to generate shear waves. Now, this technique can help you measure the Young's modulus. So what we will do is we will look over the principles behind these two techniques, the advantage and limitations of the techniques, as well as their clinical applications. In a previous lecture, we had discussed different types of ultrasound waves, and one of these waves are shear waves. So if you remember this schematic here, this animation shows what the shear wave propagation looks like, where you have particles in a tissue that will oscillate perpendicular to the direction of the wave propagation. And if we have several assumptions, such as an incompressible medium, elastic, isotropic, then we can be able to calculate the shear modulus using the following equation here, where you have G, the shear modulus, equals the density of the material times the shear wave speed to the second power. In tissue, the shear wave speed ranges on the order of 1 to 10 meters per second. And the shear modulus ranges on the orders of 1 to 100 kilopascals. So the nice thing about measuring the shear modulus with respect to mechanical property imaging is that there's a wide range of shear modulus within tissue. That way, you'll be able to differentiate between different tissue types, as well as be able to differentiate between healthy or diseased tissue quite well. Now, if you move further, you can also estimate the Young's modulus, which is denoted by this parameter E, and that equals 3 times the shear modulus. An example of an elastography image is shown here on the left, where we have the B-mode image in the bottom, and here is a color map of the elasticity estimates. Now, the scale bar is in terms of the Young's modulus, wherein red means that it has a higher Young's modulus, the tissue is more stiff, and blue means that the tissue is softer, so it has a lower Young's modulus here. So we'll go over how these images are being created in elastography. Now, I've described acoustic radiation force, and what that is a way to excite the tissue to be able to induce these shear waves. Acoustic radiation force is a body force that is in the direction of the acoustic wave propagation, and it's caused by transfer of momentum from the acoustic wave to the medium. So in an absorbing medium, and assuming that within that region there is a plane wave propagation, and what I mean by plane wave is this is in terms of longitudinal wave propagation, then the acoustic radiation force here, F, equals the power that's absorbed by the medium at a given spatial location divided by the longitudinal sound speed, C. And that equals to 2 times the acoustic absorption coefficient of the tissue times the temporal average intensity at a given spatial location in the tissue. So the intensity that we're talking about here is the spatial peak temporal average intensity. So this is the intensity that helps determine the acoustic radiation force strength. And typically in elastography, acoustic radiation force impulse is implemented. That's RFE as an abbreviation. So the RFE push pulse, as we say, is used to displace the tissue, typically on the order of 10 to 20 microns. So these are very small displacements. And what it's needed to produce this RF is a really high intensity pulse. So with an ISPT typically on the order of 1,000 to 1,400 watts per centimeter squared. To be able to produce this type of high intensity pulse, you would also need a focused beam. So a focused pulse is needed to be able to produce this force. So here at the bottom schematic here, I show you the beam profile of a focused pulse that is being transmitted by a linear array transducer right here. So you can see this is a color map scale in which yellow indicates higher intensity and blue indicates low intensity. So you can see that at the focus there is really high intensity of the wave here. And what's needed to be able to produce this focused beam is high performance power electronics. So you really need electronics that will enable you to be able to generate these radiation force impulse. Also, since the intensity is important for producing this radiation force, typically long duration pulses are used, typically on the orders of 500 to 1,000 cycles. When we talk about time or pulse durations, that's of about 0.1 to 0.5 milliseconds. So these pulses are typically much longer than what is that is used in B-mode conventional ultrasound, which utilizes about 2 cycles. Now the RF-based shear wave elastography workflow consists of the following, where first, this RF excitation is used to displace the tissue. Next, the shear wave propagates laterally away from the site of this RF excitation. So here I show a schematic of what goes on when we induce the shear wave. So first here, this is our focus push, and at the site where I denoted as red is where the RF will be applied. And then because of that RF, the tissue will displace, and then it will go back up to its original position. And because of that, a shear wave will then form that is traveling laterally from the site of RF excitation. So this shear wave will travel on both sides away from the RF excitation location. So this is similar to when you have a still pond, and you can think of the RF pulse as a drop of water. And droplet of water goes onto the still pond and creates ripples. So what's going to be forming that ripples is actually a surface wave. But if you think of what goes on inside the tissue during RF excitation, similar thing happens wherein a shear wave is emanating outside away from the site of this RF excitation. Now one can also create what's called a near plane wave supersonic shear front. And this is a type of excitation that is used in a supersonic shear imaging. So what goes on here is that you have multiple focused push beams that are being sent at multiple axial depths. So in this image here, we have different push beams that are being excited at multiple depths here, and that creates a supersonic push. It creates shear waves that are propagating from the region of the excitation, and those shear waves sum constructively along a Mach cone. And that creates a cylindrical wave that then propagates along the axial depth of the tissue right here. So this blue indicates the shear wave front that is traveling away from the site of this supersonic push. And the nice thing about this supersonic push is that now you'll be able to look into a two-dimensional view of the mechanical properties of the tissue. This will allow you to do that. After the excitation is sent, you will then monitor the shear waves, and that's typically monitored using ultrasound pulse echo imaging. Previously, focused beams were used. Until recently, plane wave imaging has gained popularity to be able to monitor these fast-moving shear waves. So what plane wave imaging does is it excites all the transducers and then creates the plane wave that is then being used to assess all the regions of the tissue within the imaging field of view. So it utilizes ultra-fast frame rates, meaning that you use almost kilohertz ranges of frame rates. Compare that to conventional beam mode ultrasound, which is typically on order of 100 hertz. In this case, we can go up to 4,000 kilohertz per second, or 4,000 kilohertz frame rates. And that allows us to capture these fast-moving shear waves. And typically, plane wave imaging doesn't have good spatial resolution. So what is typically being done is that you would angle the plane wave and sum all the echoes that are being received after plane wave excitation. And you do that after many angles. And the resulting images from the angles are then being summed together to form a final compounded image. So this is called angular plane wave compounding, and it has been used to improve the spatial resolution in plane wave imaging. After you've obtained and tracked the shear wave as a function of time, now what you are doing when you're tracking the shear wave is you're taking snapshots, beam mode images as a function of time, so you have this 3D data set, which corresponds to the lateral axial direction, also the time direction. In elastography terms, we call this in the slow time direction. And using this 3D data set, we will compute the tissue particle displacements, or the velocities, using a cross-correlation algorithm or a spatial correlation speckle tracking algorithm that will allow us to monitor the particle displacements as the shear wave is propagating through the tissue. And so here in this GIF below, I show a propagating shear wave wherein the acoustic radiation force impulse was applied at the lateral location of 0 millimeters. And after some time, the shear waves, there are 2 shear wave fronts that will be propagating alongside the lateral directions away from the site of excitation here. So you see 2 shear wave fronts that are moving to the left and to the right. Afterwards, you would look at each spatial location and compute the speed of the shear wave using some kernel-based methods. And typically, what is assumed in these small kernels is that the material is homogeneous. So there are several kernel-based methods that you would use. In this case, in this lecture, I'll just introduce you to the basic components of the elastography method, and you're welcome to look more into these kernel-based methods for computing the shear wave speed. After you have measured the shear wave speed, you can also generate the shear modulus by using our equation based on several assumptions of assuming that the material is elastic, isotropic, or incompressible here. You can also compute the Young's modulus at each spatial location and eventually generate an image such as this. So this is an image of a tissue mimicking phantom. You can see the B mode, which is in grayscale, and the overlaid Young's modulus image right here. So in this image, we see that most of the tissue, or the tissue mimicking phantom, is around 10 kilopascals. For clinical applications, typically this shear wave elastography is used to assess breast, thyroid, liver, kidney, prostate, lymph nodes. So these are all assessments that are being done in the clinic today. You can also use it to monitor thermal ablation procedures if you're doing image-guided therapy. So here's just an example on the left of a breast tumor, where here on the left is a B mode image. It's fairly challenging to see where the lesions are, or the tumors are, in this grayscale B mode image. But if you map the elastography here, if you do the elastography, map the Young's modulus using this color scale, then you'll be able to see exactly where the stiff regions are. And this stiff region would indicate that this would be the location of the tumors. The advantages of shear wave elastography is that it provides quantitative estimates of the mechanical properties. You can also image deep in the tissue almost several centimeters, and that depends on the frequency of the ultrasound. So basically, we know that there's a relationship between the frequency of sound and the penetration depth. So if you use higher frequency, then you would be able to image only at lower penetration depths compared to when you're using lower frequency. So typically, elastography is being done between 2 to 7 megahertz ultrasound frequencies. And again, this depends on the application and which organ you're trying to image. Several limitations of shear wave elastographies are that it's based on assumptions of an elastic medium, isotropic, incompressible, and homogeneous. As we know, tissues are inherently viscoelastic and heterogeneous. So therefore, there are several active areas of research to try to develop algorithms that will be able to incorporate the viscoelastic, anisotropic, heterogeneous nature of tissues. It also, elastography also requires high-end power electronics. So specialized systems are needed to be able to produce this RF to be able to excite the tissue and generate shear waves. So there are some limitations based on accessibility due to this high-end power electronics. Nonetheless, there are efforts on trying to make this system affordable. And also, some active areas of research include accounting for boundary artifacts that are around different tissue layers. As you can imagine, different boundaries can produce different ultrasound boundary effects such as refraction, reflection, and so forth. So there are several algorithms that are being used to try to compensate for that or account for it. In terms of the safety of RF-based imaging, since we are using long duration pulses and high intensity, there would be some concerns with the bioeffects of these RF-based techniques. So I'll just briefly introduce some of the safety metrics that are being used. And there is one lecture that is dedicated to safety in biomedical ultrasound. But the two metrics that I'll briefly talk about are the mechanical index, which is the potential for inducing acoustic cavitation, that is MI, and the thermal index, which is the potential for tissue heating. So typically in ultrasound scanners, in the display, you will see both of these metrics, the MI and the TI. And that will help the clinician, the sonographer guide whether the ultrasound output is within these safety limits. And so since RF methods use pulse amplitudes that are typically around 1 to 1.9 MI, RF methods use longer pulse durations, hundreds of cycles than commonly used in the diagnostic range. But systems with RF-based elastography, they are designed to function within these diagnostic limits. And thus far, there hasn't been any major adverse effects that have been reported with RF-based elastography. But keeping in mind that the sonographers always make sure that they follow the ALARA principle. ALARA meaning as low as reasonably achievable. Now for the second technique, the transient elastography. And the way the excitation of the is done is through an external mechanical vibration system. So it's another way to generate the shear wave here. It's in comparison to RF-based systems, this is fairly low cost and portable. You do not need a high power electronics system to be able to generate the RF. These mechanical vibration systems are affordable and quite low cost. And what you would need them for is to be able to generate shear waves similar to what you are seeing right here. You can see that the vibration is being done perpendicular to the tissue surface right here, and it's generating a wave that is propagating along the axial direction. So the nice thing about EMV is that you can dial it into specific vibration amplitudes, and this allows deeper penetration depths in tissue compared to RF-induced shear wave, which is limited by the depth of penetration of the ultrasound. It has been found that EMV-based techniques can induce higher local displacement amplitudes, and it requires less complex power system to operate, and it's fairly simple to control the frequency of the mechanical vibration. So what happens in the EMV technique is that typically what is done is you would monitor the shear wave, and this is what's called a longitudinal shear wave now. So you would monitor the shear wave as it's propagating longitudinally or towards the direction of the transducer here. And you would look at the shear wave at the zero lateral location here. So it's on axis of the beam. So you would track the shear wave along this axial depth at the one lateral location. This is typically known as 1D transient elastography. And a mode ultrasound is used to measure the shear wave speed. So what you are looking here is if you have a material that is on the order of 3 kilopascals Young's modulus, you would plot the A mode signal along the depth as a function of the time or slow time. All right. Now this time here is different from the time that is used in the range equation. That time basically involves the creation of the depth axis right here. The time that you're displaying here is based on the frame rates or the post-repetition frequency of the sound. So you're looking at the A mode. You're sending the signal firing, okay, as the external mechanical vibration is operating. Then you can see that the shear wave is traveling along the depth as a function of time. So typically a shear wavefront looks like this. And the way you would calculate the shear wave speed is just by taking the inverse slope of this wavefront right here. There's several algorithms that you can be able to do that. And then that can help you compute the shear wave speed. And if you assume isotropic, linear elastic, incompressible medium, then you can calculate the Young's modulus. So here, these are two different, what we call spatio-temporal profiles of the shear wave here. And you can see that the shear wave is traveling faster with time here in a more stiff material. And that's because the Young's modulus is proportional to the square of the shear wave speed. So you would see a steeper slope in this wavefront in this type of image if you have a stiffer tissue. Now this transient elastography system, a popular one that is most widely used, especially for liver fibrosis monitoring, is the system called FibroScan. Now what it does is you have a transducer here, and it's a single element transducer with a vibration capability. So this transducer would vibrate as well as receive the A mode signals that is coming from your target region of interest. And it has been a validated technique, and you can see that the system is quite portable. You can map the spatio-temporal profile of the shear wave here, and as well as it outputs the median elastic modulus fairly well right here. So there's many research articles, in clinical journals as well, demonstrating the feasibility of this technique, and so it's widely studied. The advantage of this technique is that it's quantitative. You can also image deep in the tissue quite well. The liver is more than 6 centimeters in depth, so this type of technique can be able to image deeper than RF-based techniques. It also allows for real-time imaging, and as you can see that the system is quite portable, and so it's widely used all over the world. The limitations of this technique is that it requires a lot on the sonographer's specialization, and it's widely operator dependent. This type of technique does not use B-mode image guidance, so it depends on the skill of the sonographer to be able to place the transducer at the correct location that will allow you to image the liver properly, or to detect that portion of the liver properly. It does not create two-dimensional elastography maps compared to shear wave elastography. And it also assumes an elastic, isotropic, incompressible, homogeneous medium. So these are the limitations of transient elastography. Despite these limitations, this type of technique is widely used around the world, but there are several articles that look into some limitations of the technique, which the sonographer has to keep in mind. Another important aspect of shear wave imaging are phantoms. So phantoms are widely used to be able to standardize quantitative measurements from different shear wave elastography techniques and systems. So there are many companies around the world that produce ultrasound systems with the shear wave elastography mode. And each company has their own way to post-process the data. Therefore, the Quantitative Imaging Biomarkers Alliance, or QIBA, and this is a committee of the Radiological Society of North America, or RSNA. The goal of this Biomarkers Alliance is to be able to develop phantoms that can be able to standardize imaging protocols at different regions around the world. So here I show one such phantom wherein it has the B mode imaging targets here that can help you assess echogenicity of your imaging system, your resolution. But this particular phantom also has cylindrical inclusions with different Young's modulus. So they are colored in yellow right here. You can see there's a 10 kilopascal, 60 kilopascal, and 100 kilopascal Young's modulus inclusion. And the thing with these inclusions is that they also have different depths right here. So there's another set that is located at a deeper part of this phantom. And if you take a cross section of this phantom, the cylindrical inclusions actually also vary with the different diameters. So this type of phantom will allow the researcher or system developer to be able to assess the quality of their elastography images. Now, also looking into how well the elastography algorithm will be able to define the boundaries of the inclusions, as well as how small of an inclusion can the elastography image algorithm be able to detect. So phantoms are widely used for those purposes. Now, challenge is that tissues are inherently viscoelastic, and most calibrated phantoms of known Young's modulus are considered linearly elastic. So there's a drive in the elastography field to be able to develop viscoelastic phantoms. And there are several groups that are developing shear wave viscoelastography algorithms, which will allow you to not only measure the Young's modulus, but also measure the viscosity of the tissue. So this is viscoelastography. And one such material that we are also developing in our lab is made out of polyvinyl alcohol. So this material has been used for decades, and we recently found that it has some viscoelastic properties that can be used to assess shear wave viscoelastography algorithms. So here's just an example of what these viscoelastic phantoms would look like. These phantoms you can make in the lab, and you can add some cryoprotectant of different colors to make it look like actual tissue. So here you can also, using viscoelastography algorithms, you can measure the modulus according to the recipe or the concentrations of PVA that you are inputting into your phantom, and also the viscosity. And this is one such example where the viscosity remains fairly constant, but the shear modulus increases as you change the concentrations of the PVA in the phantom. So there are other efforts looking at various types of materials of viscoelastic phantoms to be able to assess the newer viscoelastography algorithms. So I hope this lecture gives you a good overview of shear wave imaging methods. We've talked about how acoustic radiation impulse as well as mechanical vibration excitation methods will be used to generate shear waves. We also talked about how you can monitor tissue displacements using post-echo ultrasound, and various speckle tracking algorithms that can help you measure the tissue displacement. We talked about how to quantify the mechanical properties of tissues based on several assumptions, as well as different clinical applications that are being done today. There are several advantages and limitations that we've also discussed for each technique. And there are several topics of active research to help improve the technique further and make it more standardized quantitative metrics. So with that, hope you enjoyed this lecture. We'll see you in the next lecture.